All right, so welcome everybody for our second lecture on material science and engineering. And today, as I said, we got quite some interesting and extensive content for you. So I hope you would enjoy it. And let me know if you have any questions and an answer. So before we get into the content, just a few quick updates. So the first thing is try to get familiar with my courses. I mean, for students have been studying already here, I think it's something you're very familiar with. But for the exchange students, or really beginners in a way, try to get familiar with my courses because everything is updated there. All the materials, slides, assignments, and how to submit assignments, and you get your marks from there. So get familiar with it. If you have questions, don't hesitate to ask at the general discussion, in that my courses channel. If you still don't get it, visit the Q&A time. So the Q&A time is there for you to get through all these troubles. So don't hesitate and ask. The second one is I really expect very active participation. So from all of you, meaning you can ask questions, you can participate by for example, answering any questions. I will try to ask you something during the course, so make it not just I'm talking, and you could also participate. You would be able to participate even more when we go a little bit further with the course. But at the beginning, so let's say before the first half of the course, we don't have much group works. Later we will have more. But at the beginning, we don't have really some group discussion you could do during the lectures. So basically what you could participate is just ask questions and answer my questions. That would make the whole course more interesting. All right, and the third point is today we're going to do some calculations. So best is you get some pen or pencil with you, or you got your iPad. No matter what you could use to do some calculation. So let's get started. And yesterday, we already talked about the general structure or the introduction about material science engineering. And we even began, a slice of it. So as you remember, we started with the structure. So we will continue on structure. And we learned about atomic structure, electron structure, these tiny structures that you have learned basically from high school. We basically made a recap for you to get some fresh memory about it. And now we're going to build on, these tiny structures, one layer by one layer. So finally, you will realize something substantial as it is in the real world. Of course, when we do the structures, we always correlate their structures with the properties. We talked about yesterday thermal properties, electrical properties, when we talk about electrical or atomic structures. And today we will touch more. So stay tuned for that. And as I said, we will go layer by layer. So now yesterday we were talking about basically two atoms meeting each other. So today we're going to talk something a little bit more. But before we go to the atoms, as I asked you at the end of yesterday's lecture, so I was asking how to best pack orange. I don't know if anyone had thought about it. If you had, share some of your thoughts. So I will not cue anyone, but if you have some ideas, just break it out. I'm showing you one figure. So basically it's something you would buy from supermarket. This is a way of stacking. So, but we're looking for best stacking. So I don't know if you get what best stacking means. Actually, best stack means basically we need more oranges with a given volume or given space. So we are trying to achieve, if you're familiar with it, a certain density. Basically the density of orange over the entire density of the space. So that's the best stacking we're trying to look at. Is random good one? We don't know. Of course, you could have the second way of stacking. This is so-called regular stacking. So this is just 2D, you see, we're doing everything basically regular. So one orange is in touch with another 4. Yeah, this repeats just continuously. And now I'm giving you 2 more different stackings, and you can see this is 3D already, but this is nothing different from this 2D. Basically, you just put one layer up and you get this 3D regular stacking. And there's another one. I think most of you, if I gave you a certain number of oranges, ask you to stack them, you probably go with this way. Yeah, so this is naturally actually the best way to stack it, I could tell you already, but you probably need to know why. Yeah, but the way of this stacking is also simple. So you just place basically 3 like this, and you see there's a gap, and you put another one on top of it. Yeah, and that's it. If you just expand it into a whole volume, so this is something like a small corner, and if you stack to whole volume, it looks like that. So these 2 are the same. And basically the question is it the best stacking, and why? And what is the best stacking density if it is the best? I have to tell you, this is not a simple question. This is a mathematical question that drives many, great mathematicians for years. So for 4 centuries of this problem. And the origin of this problem was discovered by Mr. Walter Rayleigh. So he's a guy lived about 400 years ago, so in the 16th century in England. So he's a very colorful person. He's a politician, explorer, and also poet. You see quite many roles of him. As he was an explorer, so he was, sailing in a ship, and that was the period, England was really trying to go around the world. And one of the issues they were facing is, how could we get as many of these bombs in a shape? The shape at that time was not powerful, and the bombs are, pretty Asian. So they're just this round sphere, very regular. And he's trying to get many as possible to make it powerful, and he didn't have a good solution. That's why he asked a friend. So this friend is Thomas Harriot. You probably heard of him. He's also a mathematician, but probably you don't see many contributions of him, but he's also an interesting person. And he didn't have a solution either. So he asked another friend. So this is something you know pretty well. This is the famous Johannes Kepler, a German mathematician and astronomer. You've learned probably his laws for the planetary motion. This is from the high school, pretty nice mathematical work. So Mr. Kepler really worked on it, and he tried to solve it, and he indeed solved it, but he didn't, let's say, make a proof, but he gave answers. So his answers were given in one of the New Year's gift as a booklet to his friends and relatives, basically. This is in 1611. And in his booklet, he said, basically, as I showed you already, the best packing is looking like this. And he even gave a formal statement. So this statement was later transformed into the so-called Kepler conjecture. And it states that no arrangement of equally sized spheres, so equally sized spheres, filling space has a greater average density than that of a cubic closed packing. So this is new for you. So cubic closed packing, which is also called face-centered cubic. And so that was one of them. And the second is hexagonal closed packing arrangements. So he basically said, if we are trying to stack a equal sized spheres filling the space, the best packing or stacking is either so the cubic closed packing or hexagonal closed packing. So that was clear. And he even gave the density of it. So he gave the density of these 2 arrangements is around about 74.05%. now you're probably wondering, first of all, why these two are the best. So this is why it's a conjecture. So he couldn't give the proof, but he assumes that's the best. And you probably also wonder, how come it is 74.505%, this random strange number? And so basically, this lecture here is going to, at least the first half of the lecture, is going to walk you through. So you will be able to repeat what Kepler did after, let's say, 45 minutes from so on. And you will be also able to get this number on your own. But actually the mystery goes on, because none of these people really proved. And this brought many interest for some follow-up, mathematicians. So for example, the famous Karl Gauss, and he actually gave official proof that the Kepler conjecture is true if the spheres have to be arranged in a regular lattice. So here's a new definition. So what is lattice? Yeah, if you have something in your mind, just stay there. So we will go for a definition later. But another important thing is he solved, if it's a regular lattice, the Kepler conjecture is true. But what if it's not regular? If there's random and so on. So nobody continuously proved it until 1900. So Professor David Hilbert, you probably heard of him. He also didn't resolve this problem, but he kind of pull it off into his famous 23 unsolved problems of mathematics. Maybe you know this. And this is one of it. And he even extended to the n space as well. And there are still many unsolved mathematical problems in his list. For example, the Riemann conjecture. But what I could tell you is this conjecture was solved. And nothing has moved until about 60, 70 years ago. A French mathematician, or French or Portuguese, I forgot. So Professor Todt actually showed a significant improvement of this problem. So he said, to determine the maximum density of all arrangements, regular or irregular, could be reduced to a finite but very large number of calculations. And this means that a proof by exhaustion could work. So now I think, guys, you're getting a little bit familiar with this problem. Because Professor Todd really turned this theoretical analytical problem into, a finite problem. It's like what you're doing, for example, with FEM. What you're doing with FEM, basically you have a bunch of differential equations, and you cannot solve it easily, with your brain, with pen and pencil. And that's why we're going to make approximation. We're going to make that into a finite stacks of linear equations and so on, and try to solve it. And this is not exactly the same, but very similar. So he said, if we're going to make this proof, we're going to do a finite number of exhaustion. And he even gave a clue about it. And this was the key. I have to tell you, this was the key. And basically, many mathematicians followed his approach. And this conjecture was just recently proved. So I will not tell you right now who proved it, how. I will leave that till the end of the lecture. So just stay tuned if you're curious about it. That was enough for a historical, let's say, issue and basically a story to open our today's lecture. We're not going to talk about oranges or spheres. Our lecture is going to talk about atoms. So you remember when two atoms meeting each other, what happens? But today we're going to talk about if we have, a group of atoms meeting together, how they will be arranged, in terms of their space orientations. So very easily, as we talked before, like orange, there could be random packing or there could be ordered packing. So ordered packing means something regular. I could already tell you our atoms in most of the materials, they would prefer ordered packing. And the reason is pretty simple, because we already showed you this, this energy versus radius or distance between between the bond length diagram, our atoms always prefer to go with the lowest energy. This is nature. And roughly speaking, when we have the random packing, you can already see the random packing is not giving you the highest packing density. And with this higher distance, this loose density, you are actually increasing the bond length. That will lead a higher energy in the end. On the contrary, if we go with the closed packing or ordered packing, basically we're coming closer to this lowest energy minimal. So that is the reason basically why our atoms are packing mostly in ordered way, and because that will make the material stable. So that is the reason. And that's why today we're going to tell you why and how they are packed, and how could you calculate, their packing density, and how could you really understand the influence of those packing to the material properties. So these are the few, let's say, concepts. So don't be surprised by all these terms at the moment. We will explain you just one by one. So here is first the difference between the crystalline and non-crystalline solids. So we'll tell you later what is difference between them. And then what are the very typical crystal structures of metals. And we take example of metals from our materials family. And what are characteristics of this kind of crystal structures. Characteristics means, their packing density, some numbers I will show you later. And the second thing, these are all, let's say, qualitative description. And the more important issue is we want to give a quantitative description. So if we stack orange, we don't need to identify, we don't need to label which orange is which. But if we speak about atoms, we need to know actually which is which and what is their directions, what is the plane. You will now, at this lecture, know how to do this, but you will not know probably why you're doing this. And the reason for that will be given basically in the follow-up lectures. And finally, you will build up the link between, let's say, an arrangement of atoms with their certain mechanical and even other properties. All right, so first, some definitions. What is crystalline materials? Actually, it's pretty simple. Crystalline materials, or you could also call it the crystal materials, means your atoms are stacked in a periodic and 3D arrays. So that is nothing but it's a regular packing. So one example is given here by this silicon oxide. You see, it is periodic and it's in a 3D array, basically meaning you could repeat it in a space with a certain unit cell. Yeah. So another term is called a unit cell. Don't worry, you will also get definition later. And typical crystalline materials are metal. Yeah. Almost all the metals are crystalline materials, and many ceramics and some polymers. So you see the crystalline materials are really taking a large fraction of existing materials. And that is why, that is the reason, because, atoms naturally tend to go with the lowest energy status. That is leading to a regular packing. But we also have some non-crystalline materials. So basically, this is the same silicon oxide. With some forces, you could break their crystalline structures. So here, as you can see, this part is distorted. And some materials could have this. So the definition is they don't have a periodic arrangement. And the reason for this is usually not nature, but by force. So for example, one of that is something called rapid cooling. Not now, but later you will learn with the rapid cooling, our materials will not get a so-called equilibrium status. So if everything is in the equilibrium status, your materials tend to go to the nature status, which is the minimum energy. But if it's not in the equilibrium, you put kind of energy into your material, that will lead to something with a little bit higher energy. So we will talk about that. And so the non-crystalline materials could be also called amorphous materials. So they're the same. When you just meet these words, don't be surprised. They mean your crystal, your materials is not in a regular or a periodic arrangement. So that's some very simple definition. I could also give you some reason concerning why metals are preferring or could reach, let's say, the crystal structure, with the dense packing or regular packing. So one of the reasons is, the metallic bonds we have learned before is a little bit different. It is creating, due to the electron cloud, a kind of non-directional forces among all the atoms. Yeah, so that is very beneficial. Yeah, that is beneficial for materials to just repeat each other. If you have certain orientations, that always creates, certain kind of forced arrangements. That's why not all the, let's say, the ceramics could have the close packing. And there are also two more reasons are listed here. You could also know a little bit details about them. But the first one is the major reason actually for metals having the dense packing. And that's why, so just for the simple reason, we're going to go with the metals first, because they have very simple structures in terms of closed packing or dense packing. Ceramics also have even some polymers. We will touch, those two materials a little bit later in this course. Now let's go to our crystal structures of metals. Now you will basically learn all these different packing rules or packing arrangements. The first one is so-called simple cubic crystal structure. And this is something everybody knows pretty well. Yeah, that's basically the first ordered packing I showed you with the oranges. Yeah. And this is easy, so I don't even need to explain that. So these three figures are basically displaying in the same, the packing is just one in the center, and you locate four as neighbors, and then you have a regular pattern, and then just go up and go down and so on. Here I would like to give you two very important concepts. The first one is so-called lattice. I promise you I will give you a definition about it. So what is definition? Lattice is atomic arrangement can be described to a network of lines. So two things. So first is atomic arrangements. Atomic arrangements means you need to have atoms. So these are the so-called points. And it could be described to a network of lines. So that means you have network of lines. So this is important. And this is a definition of lattice. It could be regular, it could be irregular. So that doesn't matter. So lattice is just a framework in 3D, by the way. And the second one is so-called unit cell. We already mentioned about it. Now you get a definition. So unit cell is the smallest repeating entity of the atomic structure and the base building block of the crystal structure. So that's why this is the kind of overall picture. And I'm giving you such a picture here. So this is the so-called unit cell, because if you just take this one cube out of here, then you could have the entire space by repeating itself. Yeah, this is so-called unit cell. And these two actually are identical. And we're drawing this way just to, to keep it simple. But actually in the real atoms, they're packed in such a way. Yeah, so this is the so-called hard sphere packing or hard sphere drawing of your atoms, but it's rather difficult to draw in many cases. So we do this in many textbooks and so on. But you need to realize in the reality, your atoms are really so close to touch to each other, because this will go to their minimum energy status. All right, so if we just try to realize these two concepts in this simple cubic, so these are so-called lattice points. And here, this is the unit cell, you know, all this. Now I'm going to go with some simple characteristics of this simple crystal structure, simple cubic crystal structure. As you can see, the first question I'm going to ask you is atoms, the centers of atoms located here, basically not one atom, you know, it is not belonging to one unit cell, let's say. It is actually belonging to, if you just realize it's belonging to 8 unit cell. This is important because it will be related to other characteristics you're going to do later on. So this atom basically is shared by, you know, 4 unit cells here, or 4 cubes bottom and 4 cubes up. Yeah, this applies to every, let's say, atoms here. So this is the first feature. And the second is the simple cubic crystal packing is really not popular. As you probably remember, this is not the most dense one, it's just ordered. And that's why not many materials have this kind of packing. And actually there's only one, this is the PO, is having such a simple cubic packing. The second feature about this, let's say, simple cubic crystal is we're trying to locate what is the closed packing directions. So this is important because we want to know how you're packed. And for this one, it's actually rather easy, as I showed you here by this animation. They closed packing directions are, so I here showed you 3, but actually you can draw many, but they're just repeating each other, right? So these are the 3, let's say, axis, X and Y, Z. If we have a coordinate system into this simple cubic crystal structure, and these are the edges of it. Meaning, if you just go to the diagonal direction, yeah, you will not have the closed packing direction because it takes more space or more distance to meet the second elements or the second atoms. That's why this direction is the closed packing, because you need the minimum distance to reach the second atoms. The last concept or characteristic about the simple cubic packing is what is so-called coordination number. So first of all, what is coordination number? So coordination number is basically the neighbors of one atom in touch with others. So basically, we're looking for the nearest neighbors of the atom here. So as you can see, if you want to get this number rather clearly, you need to know what is the closed pack direction. Yeah, if you probably look at it here, it's easier. Yeah, because the closed pack directions are these edges, you're easily arriving, let's say 6, right? So you have 4 in the same plane and 1 up, 1 down. And this one, so for example, this one is not your nearest number. That's why it doesn't take into account when you calculate the coordination number. So these are 3 very important characteristics. They're important because you're going to need them to calculate your packing density. Now I'm going to introduce you what is the packing density. So the first definition is about the coordination number. We have already spoken about it. And the packing density is also defined as atomic packing factor. If we were talking about atomic arrangement, this is so-called APF. Yeah, and the definition is pretty simple. Actually, you could imagine it. It's basically the volume of atoms in a unit cell divided by the volume of the unit cell. So this is pretty easy, right? So I repeat here. So the volume of atom in a unit cell and divide by the volume of the unit cell. So the unit cell should be a little bit emphasizes because here we're talking about the hard sphere unit cell. So the first figure I showed you here, not this one, because this is the reality. Yeah, just remember that. Okay, so with this simple definition, actually we could do some calculations already. Yeah, because the first thing you need to get is the volume of atoms in a unit cell. So how to get the volume of atoms, basically you need to know how many atoms are there in a unit cell and what is the volume of a unit cell, right? What the volume of an atom. Yeah, now I'm going to show you some, let's say, examples or calculations. So we start with the simple cubic packing. You see, if we just gave a distance of A as our unit cell, the edge of the unit cell, and you could see already easily get the volume of the unit cell. It's A cubed, right? Now we need to work on the upper part. So what is the volume of the atoms? So first, as we said, we need to get what is the number of atoms in such a simple cubic cell. I think everybody could already imagine, yeah, it is probably you could get it. I will not ask. It is one atom. Why? Because we have, you know, basically 8 parts of an atom here, but this part is not the full atom, as we already spoken about. This atom or this part is shared by 8 cubes. Remember, yeah, this part is shared by 8 adjacent unit cells. That's why this is only 1/8 of an atom. So if you just calculate 8 by 1/8, then you get a full atom. So this is the first part of the simple cubic. Yeah, you have 1 atom per unit cell. And now we want to get the volume of atom. So that's rather easy because you're going to look for the closed packing direction. Yeah, you know the closed packing direction is that. So the whole length here is A. The radius of your atom basically is half A. So that goes here. And by some simple formula, you already get it. The volume fraction or the packing density of simple cubic is 52%. Yeah. So this is the way how you're going to do it. I don't think we have time to do some practice now at this course, but you will have the chances to practice it, yeah, in your assignments. Now I'm going to move forward to the second cubic structure, crystal structure. That is the body-centered cubic crystal structure, so-called BCC. And actually, with the knowledge you have already on simple cubic, this is rather simple because it's nothing but just adding one central element or one central atom to your simple cubic structure. You can visualize by the hard sphere model here, or this kind of lattice model like here, and something like this. Some typical examples of this structure is chromium, you know, and alpha iron. So maybe wondering what is alpha here, and this definition or reason for this will be given later of our courses when we just go to the phase diagrams and so on. And many metals. So this is one of the most popular, let's say, crystal structures already. Now we're going to go with some simple numbers or simple characteristics. So I'm going to ask you first is what is coordination number? Yeah, so I have to give you, it's 8. It's very easy to get it because if you just take the atom in the center, how many atoms are this guy's nearest neighbors? Yeah, you can easily say it's 8, yeah, because the 8 corners. You will arrive the same if you just take a corner atom. So I will not tell you, you can just practice on yourself and you will arrive the same. And more importantly, we're going to need to calculate how many atoms are in this unit cell. Remember, this is important because finally we want to arrive their packing density and the APF for atomic arrangement. And maybe you have some idea, like take a look at here. Okay, we have 30 people, not bad. But I'm going to give you the answer right away. Maybe remember, if we just have a simple cubic, we have 1 atom. Now, basically, you add another one in the center. Is this atom shared by any other unit cells? No. So that means we have 2 atoms within this unit cell. So I'm already giving you here. You should pay a little bit attention on this drawing. You know, some students probably wondering, you know, these 2 atoms don't look like the same. You know, the center element is much bigger than the corner elements. The atoms, that's true. That's just the rendering issue. So don't mind, just imagine everything's the same. And the corner atoms is in touch with the center element. All right, good. Now we're gonna go to the calculation about packing density. So if you manage this, you are already very close to Kepler. You know, some very challenging thing 400 years ago. Now you could try to get it. As the regular business, we need to know what is, we already got it, how many atoms within this unit cell. We basically need to know the, let's say, the volume of the unit cell and the volume of our atoms. And this is a little bit challenging than the simple cubic crystal structures, because here you need to first figure out what is the closed packing direction. It is not the edge anymore, because you see, if we go from here to there, we're gonna not meet our atoms directly. And it's also not the plane diagonal, because you're gonna not meet your atoms also directly. And now you probably imagine the closed pack direction is the volume diagonal. Only in this way, you're meeting your atoms like right away. And for this line, we actually have, let's say, if you can imagine, 4R. You have half R, another half R, and you have a full 2R here. So sorry, you have 1R, another R, and you have a 2 R's, a full diameter of your atom here. So that gives us a first clue how to convert or correlate between the volume of atom and the volume of the unit cell. So basically this 4 times R is equal to square root of 3 times A. Now you can express your R with A. And the same mathematical treatment as we did before. We know the atom numbers per unit cell. We know the volume of the unit cell. Now we also know the volume of the atom. And here's the number. So you don't need to calculate it on your own. I'm giving you it. It's 68%. You see it's closer, and it's closer to the Kepler conjecture, but not yet there. So what is the best packing? So this is the line. It's face-centered cubic structure. It's very simple as well. As you remember what we did with body-centered, we put a atom in the center of the body, in the center of the unit cell. But now we're not putting it in the center of the body, but we're putting it on the center of each face. So we're adding a half of the unit cell of the atom to the 6 faces of our unit cell. If you can look at in this picture, maybe it's more vivid. You see, this is how it is done. And here I'm going to ask you again, what is coordination number? This is a little bit challenging. It's 12. Once again, you can arrive this number either via the corner element, the corner atom, or via the face atom. So both will work. Just try to practice your own. What is the coordination number? More importantly, we need to know how many atoms per each unit cell. And I'm giving you the answer directly. So we have 6 half atoms, as you can see. The face element atom is shared by another unit cell, so that's why it's half. And we also have the 8 corners of 1/8. Basically, this will give us 4 atoms per unit cell. Now you got it? Good. And now we calculate the, let's say, the packing density or the APF. So same business. Now we need to find out what is the closed pack direction. I'm also giving you here, because the atoms added on the face, you can easily figure out the closed packing direction actually is the diagonals, the phase diagonal direction, and some simple mathematical arrangement again. So 4r is equal to square 2. So sorry, this square is a little bit off place. So square 2 times a, and then we can express our r with respect to a. And if we go with the same formula as we used it before, as you can see, the magic number is here. This is 74. If you go a little bit further, it's 0.5%. And here you go, guys. Now I go with a rather, let's say, fast pace, but I think it was pretty clear for everybody. And now you get it. Now you know how to calculate the closed packing density and what is it. Let's go a little bit further with this closed packing density, because you can play with the sequential of it. So why we could play with it, as I can show you here. If we just put our atoms not like in the unit cell, just expand it in space, you can see we can just close pack it in, let's say, one play like this. And this is already close packing, by the way. And now if we go with the second layer, as you can see, this is the A size. And we're going to go the second layer as blue. So you don't have any choices. You go with B here, and so on. And the interesting part comes at the C sides. So as you can see, I can put my C here, yeah, and I could also put my C here, right? It's just a choice. If you go with here, you can see the C is basically repeating A. Yeah, you realized it, right? If I put it here, it is exactly the same as the green one on the bottom of the blue. But if I put it here, it's a new kind of pattern. Yeah. So this two different kind of packing sequences actually leading to why Mr. Kepler is giving us two configurations. And we studied about the phase cubic kind of packing. And this is actually what I could tell you is this ABC packing. I show you here. So now you see the connection. So this is something like we're going with the space, but if you just try to reflect it into the unit cell, you know, the diagonal kind of orientation or plane of the unit cell is the so-called closed packed plane. And you just go above it. You go, that is A, and the other diagonal is B, and this corner is one of the C. And for the FCC structure, you are basically repeating this ABC kind of packing. Now you're probably wondering, what is the, let's say, the second packing? This is so-called hexagonal closed packing. This was also given by Mr. Kepler. And this is exactly the AB packing. So as you can see, this is our A, and this is B, and the kind of C is exactly repeating A. Yeah. The difference between this kind of HCP, so hexagonal closed packing, is the unit cell. So the unit cell for the HCP crystal structure is different from the FCC. Yeah. So I'm not going to go to details into this part because you probably need to, you know, solidify this stuff in your master course. So we rather focus on the FCC structure. So, but you need to remember the unit cell for the HCP is different. It's rather a hexagon than a cube. Yeah. But what is the same in common between these two structures is they have exactly the same coordination number. They have exactly the same packing density, the APF. Yeah, that's why both of them are the closed packing structures. All right, so that is enough for these three very simple but interesting crystal structures. Now you get all of them. And now we would like to make some reflection about this packing, let's say, arrangements with respect to the properties. So one of the properties I would like to draw your attention is density, because actually, you know, we always measure density, Yeah. But if you know now how the atoms are packed, and if you also know what is the mass of your atom, you can already calculate the so-called density. It is the so-called theoretical density. It's not that difficult. Yeah, you have all the knowledge already. So once again, what is density? So density is a certain mass over a certain volume. Because our metals are, let's say, regular packed, if you just calculate a mass of your atoms in a unit cell, divide by the volume of the unit cell, and then you know the global density. So we can get this from a unit cell and just extract it to a global density. And how to get that? And this is pretty easy, right? If you know already the atomic weight, yeah, this is the capital A, maybe you remember. So atomic weight of your atom. So this is something everybody knows, yeah. So for carbon, it's 12 grams per mole, yeah. But this is too many, so we need to divide it into divide the Avogadro number. Now you get the kind of. So somebody wants to give some comments.
I'm sorry, I forgot to mute mine.
Okay, I thought you want to answer something. No problem. If you have questions, don't hesitate. It's definitely okay. Where was I? Okay, I was telling you how to get the mass of a atom. If you know the atomic weight, and if you just use the weight divided by the Avogadro number, you get the weight of an atom. Yeah. And how many atoms are in your unit cell? N. So N times that number divided by the volume of the unit cell. So this is the simple equation. So remember this. You will need this to do certain calculations in later. You could do some practice on your own when you get more time. Here I'm giving you directly the answer. Yeah. So as nodes, you know, A. So the example is given for chromium. It's a BCC structure. So you know chromium, the A, and you know also the R of the atom radius. And you also in BC structure, you have 2 atoms per unit cell. And then you have certain simple arrangements by using that equation we just derived before. As you can see, you arrive to a density. It's 7.19 grams per centimeter cubed. I don't know if anyone has a density impression about chromium. What I could tell you is this density is pretty close already. Yeah, not exactly the same, but pretty close. So remember this number. I will ask you why it's not that exactly the same as we measured. Yeah, one hint for you is this is the so-called theoretical density. Yeah, good. And then you can see some, density correlation to our materials of different categories. And for example, for metals, you can see they're always the heaviest. One reason for that is they're having the close packing, yeah, for metals, but also often they have rather large atomic masses. That's also the second major reason for metal being so heavy. And the ceramic is second, and the polymers third, and composite is something a little bit in the hybrid way. So as you can see, you can have a impression from this diagram here. The second property we're going to refer to is the, let's say, anisotropy. It's mechanical. So here I'm talking about elastic. Yeah, everybody knows what is E modular, right? What is stiffness? And as you can see, due to this atomic packing, we would already have some anisotropy. Meaning, if we just pull our material with a force in this direction, the result will be different if we pull it in this diagonal direction. Yeah, I think you know, because the atoms are much close in this direction than that direction. If you remember, the bonding mechanism, you need a little bit more forces to move your atoms if we just go with the close packing. So this is easy to imagine, right? So the anisotropy gives you some hint that the E modular for material is not a number, it's rather a matrix. So it depending how you put it. But actually for many materials, it is not an anisotropic, it's either isotropic. So we will just give you Y and N of this lecture today. These are the two properties about, let's say, influenced by the packing arrangements, and also some examples about crystals, about metals. So we talk about, how packing is done, and this is something very, very similar as a closed packing, let's say, material. It is a single crystal. So here you probably remember what is crystal. Yeah, crystal is just the atoms within a ranging that is just repeating their kind of packing, repeating their unit cells. Yeah, and by single crystal means, in this whole kind of turbine blade, this whole component, your atoms are regularly just repeating. So there's nothing but repeating the unit cell. Yeah, from the bottom to the top. Yeah, you don't see the atoms, but they're just repeating itself. So this is very pure, yeah? And this is very rare to get. Diamond is a single crystal, if you remember. It is that pure because it's a single crystal. Yeah? It's very regular. So that's all about our crystal structures and some characteristics. And I also gave you some, let's say, mechanical properties. Now we're gonna go quickly to some characterization of the crystal structures. And then we're gonna go to a small break before we go to the second half of the course. As I said, we do not only want to know, the packing density of our oranges or of our atoms, we also want to know where is this atom and where is the other atom. Basically, we want to label, we want to give quantitative description of our atoms, of an area of atoms, of a plane of atoms. You probably wonder, why do we need to do that? Because they're just repeating. Yeah, as I told you, you will not know why, but you will know why just next week already. And there's very interesting reason for why. But for today's lecture, I will tell you how we're going to do that. Yeah. So first of all, we will go with the point coordination. Yeah. So if we want to identify one atom in a unit cell or in a coordination, how we're going to do that? So that's something actually you could easily know. Basically, we just construct a coordination system, in line with our unit cell. Yeah, that's simple. For example, if this is the unit cell with the edge length ABC, so ABC, they don't need to necessarily equal to each other, but they could be also equal. If they're equal, we're facing something like simple cubic, BCC, FCC, all the structures. So for just simple reason, you can imagine they are the same. Yeah, but here I'm giving you as if they were different. We have our coordinate system X, Y, and Y, and Z, along with A and B and C. If now I want to know, well, how should I describe this atom? So here I'm giving you a procedure. So we just try to identify the lattice position of this atom. So easily, it's A and B and C, right? Simple. And we don't want to see actually A, B, C because it's boring. You always need to give certain number. If A is 2.5 micron, you need to write 2.5 micron and so on. So that's a little bit not that easy. And that's why we're going to do a division. So we're going to divide this lattice positions in coordinates by, the length of each edges respectively. Yeah. So meaning we're normalizing it. So we're going to go for A, A direction divided by A and B divided by B, C divided by C. Actually, this atom, we will call it simply 111. Yeah. So I hope you get it. And if you don't, you can make a practice later here. So this example, I only included for you to make practices on your own. So I'm showing you the direction finally, the results finally. But after this practice, you will not only get a point coordinate, actually you will also get a direction coordinate. Because for a direction coordinate, what we need to get is first the point coordinate. How do we do that? So we're going to start with the origin. So this is the tail point, point 1. And we find the point coordinate of the second point. For example, here, this is the head point, and this is point 2. What is the point coordinate of this guy? And this is the, as you can see, and here it's A and 0 because we don't have any Y, and it's half C in terms of Z direction. So the point coordinate for the head point is A0 and half C. And how do we describe this direction? So we will basically use the head coordinate minus the tail coordinate. So the equation is given by here. And after we get it, we're gonna do a kind of normalization again. So we're gonna divide this kind of length by A, B, and C again. So as you can see, finally we arrived 1, 0, and a half. And the last step is we don't want to have, half here. We want to have integers just to make things simpler. And then we're going to try to find the smallest integer value. And this is becoming 2, 0, and 1. The final step is we write it, without these two commas and in bracket, square bracket, and this is called 201. So to describe this vector, so this direction like this with a complex vector or matrix, we're going to just simplify it into 201. So this is the direction of 201. If I say we need to find the direction of 201, we're talking about this one. And why we're using this certain convention, because Mr. Miller defined it first, and we call it the Miller indices. So that is the crystallography direction. So let's say the one-dimensional thing. You could do a little practice on your own and to find out what is the Miller index of this direction. Yeah, just to follow the same procedure as I showed you before. So we're gonna not go to here step by step, but this will be given to you after you receive the slides. What I wanted to tell you is we need to pay attention to a certain so-called family of directions. Because you will soon realize, for example, if we just take this small unit cell here, if we just go a direction like this, from the origin to this point, or we go from origin to that point, or from origin to this point. Actually, if you imagine if we are doing it within simple cubic or BCC or FCC, these three directions, mathematically, they're different. Because here it is 100, and here it's 101, and here it's 001. But physically or crystallographically, they're the same. Because our units are repeating and they're equal. So you don't make any differences. That's why for certain specific directions, like I just showed you, 100, 010, 001, and even if you go just opposite to minus, so this minus, this small roof here is indicating minus. They're all equal. So for this kind of equivalent directions, we gave a different indication about it with this, how it's called, this is short bracket, it is called 100. So this is a specific direction, and this is a family of direction. So I hope you realize that. And here I'm giving you some common, let's say, crystallography directions here, and you can see those directions. And the last point is about the crystallography planes. Actually, if you know what is the correlation between plane and direction, it's rather simple because we usually use the normal of the plane to characterize a plane. So the normal of the plane is a direction, right? But here I'm gonna anyway show you how we do it. The procedure is also simple. The first step is we need to find a unit cell or coordinate system that is not passing, the origin of which is not passing the plane. So because we are having a repeating system, if your origin is on this plane, you move it, yeah, you relocate it. And if you want to now characterize this blue plane here, we don't need to move anything because the origin is there, so everything's fine. But then we can go to the second. The second step is we need to try to find the intercepts of this plane with our coordinate system. So for the x-axis, you see this is A, and for the y-axis, you see this is B, and for z, there's nothing. It is kind of infinity because it is in parallel with the z-axis, right? And the third step is easy. We just reverse it, and we need to find, we'll get this 1 over A, 1 over B, and 1 over infinity. What is that? Yeah, that gives us actually 1, 1, 0. Yeah, so 1, 1, 0 is after the normalization, as you can see. Here, we always do the normalization as we did for the direction and point. So finally, we're going to get 1, 1, 0. The reduction is if there's, again, a fraction number, you will try to find the smallest integer as we did for the direction. And here we put it into the Miller index. It is 1, 1, 0 with a round bracket. And that's it. But if I just gave you a hint, if you try to find the normal of this direction, actually you would already realize the direction is 1, 1, 0. So as I said, the plane direction is rather easy, and you have two ways to find it. If you're very good at finding the normal, go with normal. And this is another example for you to practice on your own. I'm going to not explain you in detail, but the same procedures apply here. And even the third one, a more complicated one. So you can see it's very constructive. You can just go for it. And the same concept, I need to introduce you here also. We have a family of planes. It's exactly as the directions. Yeah, for example, here I can give you an example of, once again, this, let's say the 100 plane here, and 010 plane here, and also the 001 plane here. They're mathematically different, but crystallographically, they're the same. So we call them the family of planes. You try to think about how many, individual planes in a family of planes. Of here, I'm giving you 100, but you can also go a little bit further. Good. And this is just telling you in the unit cell. We were also only speaking about in one unit cell, but if you just repeat your unit cell, actually everything could be already found for a common space when you just try to use everything in a unit cell. All right, I think that was a little bit longer than I expected, but finally we arrived at our first half of lecture. So if I just gave you a quick summary up to now, we actually get the point that atoms could assemble into crystalline, so meaning ordered arrangement, or amorphous, so meaning disordered structures. So we have certain examples for crystalline materials and a certain example for the non-crystalline materials. And for metals, all of them are basically crystalline materials. And you have also learned some few very simple or common, let's say, crystal structures. There are 4 in total. So a very rare one, simple crystal, a simple cubic, sorry. And then we have the BCC, FCC, HCP. And you also learn many characteristics of them. And you learn also basically how to calculate the best packing density, as Mr. Kepler did in his booklet. And the third point is we learn how to quantitatively describe crystallography points, directions, and planes. You learned the procedures today. You didn't learn the reason. I will give you the reason next week. And the concept for doing this is demanded by Mr. Miller. That's why we call this as Miller index. You also learned this, crystallography orientations or crystallography arrangements of your atoms would make already impact to your properties, especially on density and mechanical anisotropy in elasticity. All right, that was a quick summary of the first path of the lecture. Now let's have a short break for about 5 minutes as yesterday. Everybody can go out for a fresh and get a coffee or something. We will continue in 5 minutes. See you later. All right, guys. I'm back. I hope so are you. And we're gonna continue. So we had I hope everybody had an interesting journey so far to learn, something very specific, but also something in general about mathematical issues. You're probably still wondering who proved that Kepler conjecture. So I will give you this at the very end of the course. But before that, we're going to go to something a little bit different in terms of material science. Now let me get my laser point. Maybe you remember this issue. I asked you about the theoretical density of chromium. You made the calculation based on the, let's say, assumption of BCC structure, or let's say a perfect BCC structure. And you get this value, 7.19 gram per centimeter cubed. I can tell you, in reality, the actual density of chromium, let's say at room temperature, is 7.15 gram per centimeter cube. Maybe you see I added a term at room temperature. Yeah, actually this is the key. Why the density is different after our theoretical calculation with the actual measurement. So the key was we measured things at room temperature. And I can tell you why. This is not something is related about thermal expansion, that's true. But another issue is really related to the concept I'm giving you right now. It is something about imperfection in solids. So when we speak about the crystal structure, arrangement, packing, we're doing everything as if they were, perfect. We have all the atoms that are equal sized and they're everywhere. But after this lecture, you will know, actually from life, you probably already know, nothing is perfect. And we will basically get why and what type of, let's say, defects, imperfections exist in our materials, in the solid materials. And we're going to learn this type of, let's say, imperfections in a also similar way as I showed you. We're going to start with 0 dimension, 1 dimension, and 2 dimensions. So there are some specific terms. Once again, what is the solid solution? What is dislocations? You will basically learn them while I'm walking you through the rest of the lecture. And more importantly, I'm trying to tell you why there are imperfections. This is related to temperature. Yeah. Finally, I will try to tell you those imperfections will make an impact on the properties as well. And they even make a very decisive influence on our mechanical properties, especially. All right, let's just get started. So, as I told you already, we don't have perfect crystals, as we don't have a perfect world as well. And there are always imperfections in our crystals. And surprisingly, many, let's say, properties, especially mechanical properties, are decided by these imperfections. Yeah, I will tell you why in the later lectures. So the question here on the following up content will be basically telling you what kinds of crystalline imperfections exist in solids. Basically, there are 3 types. So as I told you already, we have the so-called point defects. This is so-called 0 dimensional. Maybe this is something you can easily imagine, because when I was just showing you the perfect crystal of BCC, FCCs, and so on, we assume, all the atoms are just sitting there. No one's missing, no absence, but, not everyone is always there, right? So the first type is vacancies. If one atom missing, if a couple of atoms missing, they are so-called vacancies. And there could be also the cases, the atoms are in different positions. So they're called interstitial atoms. I will show you figures. And there also could be a case a perfect iron atoms is replaced by a chromium atom, you know, and this is called so-called substitution impurity. So you will learn examples. Basically, there are 3 point defects. That's something you could keep in mind. And then we move on. We go to the kind of one-dimensional defects. This is the linear defects, and the kind of representative is dislocations. So you have a understanding about dislocations from your daily life. Yeah. So the dislocation in the material science is something similar. The meaning is quite similar, but we will give you proper definitions later. And then we move to the 2-dimensional kind of defects. They are interfacial defects, so they are planes. They're not about line anymore. And here we have 2, or let's say 3 types. They're grain boundaries, twin boundaries, and stacking faults. We will rather focus on the grain boundaries. So you know there are other 2, but we will not address them. If you're interested in it, you can read from the book. I'm sure if you go with mechanical engineering or material science engineering in your master course, you will get a lot about this. All right, now let's go one by one. So first about point defects and how to visualize a vacancy. Actually, that's simple. So here you see this atom is missing. It's a vacancy, but it's not like a vacancy has no influence. You know, in our materials, once there's something missing, due to everything is bounded with the forces and so on, it will cause some distortion of the whole plane. Yeah, this is some consequences. And there's a similar thing if we're talking about the same atoms, if we're talking about pure material. Yeah, you know, if this guy is missing, not just missing for good, but he just jumped into a different position. So it jumps into a position he shouldn't be. And this will create a so-called self-institution. So basically he's here and causing, once again, some distortion of planes. So this is so-called self-interstitial. And this is the first example. Now I'm going to tell you why we're having vacancies in the world. As I told you, this is related to the facts that we don't have a theoretical density of our materials. The really fundamental reason is a little bit beyond most likely your current concept. I mean, maybe for some other students who are joining us at a rather late program after your master, or you're even joining from from your late program of your bachelor, or you're also joining from your master program. You know, this is the whole thing is driven by the thermodynamics, the second law of thermodynamics, to be more specific. The second law of thermodynamics is something a little bit hard if you didn't learn the theory, but I think everybody knows their kind of implication, because the second law of thermodynamics basically tells us the whole universe is going to chaos. Maybe you know. If you don't kind of give a certain force to a system, the nature case of system is going to chaos. It's going to something like, you know, hate kind of participation. What does that mean? So that means if we talk about the crystalline of our materials, that means we will have a certain disordered things in our crystals, because, you know, things are going to chaos. And that's the reason why our materials are having imperfections or having vacancies. There's one equation. I'm not going to tell you how this equation is derived, but you can use this equation to understand the second thermodynamics law. So if we just try to describe the fraction of the vacancies, so using the number of vacancies divided by the total number of lattice sites. So if we have volume, we assume it's BCC, and we know how many lattice sites should be there. Yeah, and you can see this is telling us a fraction of our vacancies. And this fraction is basically dictated by this expression. It is an exponential function. And first of all, you have one quantity. It is so-called activation energy. This is a quantity you could measure from experiment, and it is decided by the enthalpy and entropy that relate to the thermodynamics. We will not touch it, so you know this is a material specific quantity. That's enough. It is a measure, basically, of the extent of these atoms are going to chaos. Yeah. More importantly, you should pay attention to here. So first, we have a constant. This is the famous Boltzmann's constant, and there's a temperature. Yeah, this is the point. Let me just give you some graph here. As you can see, we can plot this graph into a simple exponential. If we take our y-axis as the fraction of x of vacancies, and if we take the x-axis as temperature, and everybody knows how the exponential function looks like, I just would simply ask you a question. If you just assume, you know, the term within this exponential function, if this term goes to negative infinity, what will happen? Yeah, basically, if you just go the negative infinity of this exponential function, I think everybody knows, you will reach zero. You're approaching zero, right? And that is the point giving us, you know, a fraction of vacancies. Zero means you have no vacancies. So maybe now you're wondering, what is the condition for a perfect world, for a perfect crystal? That is this part going to infinity, negative infinity. How it could go to negative infinity when the temperature becomes zero? So this is the so-called absolute zero temperature if we go with the Kelvin measure. And that is also why, maybe you know, at absolute zero, we will have some super interesting phenomena. For example, the superconductivity. Basically, you have no electroconductivity at absolute zero because, you know, everything is perfect. As we have temperatures, that means the world is not perfect. All right, so I think that gives you a good explanation. You could probably figure out many things. You can also use this as a metaphor in many cases. Yeah, for example, when you're angry, your temperature rises. Yeah, when you're emotional, your temperature rises. So this is somewhat, you know, dictated by this second thermodynamics law. You can also play some mathematical tricks just to do in log kind of calculation of these terms, and you will arrive a linear curve, and just for you to better visualize it. But I hope you get the meaning of it. And with this concept in mind, I would like to ask you basically calculate. So we know there's certain volume fraction of vacancies, but how much? Yeah, you want to get some numbers. Yeah, you want to get some feeling. Here I'm giving you an example. If you want to calculate the number of vacancies for a 1 meter cubed of copper at 1000 degrees C. Yeah, could be a tricky question because you first need to know what is the status of copper at 1000 degrees C. Yeah, so maybe you know copper has a very high melting temperature. So with 1000 degrees C, it's still in solid. Yeah. And here I'm showing you how to do this calculation. It's just using the equation I told you before. So before we calculate, first we need to know what is the number of the lattice sides in the 1 meter cube copper. And how to calculate that, we need to basically use our Avogadro number again, because you know density of a copper. And if we just use this density of the copper divided by the or times the Avogadro number of the copper, you basically know the kind of volume fraction, and then you just try to divide it into this the atomic weight. You will get basically the number of the lattice vacancy, the lattice sides within 1 meter cubed of copper. And afterwards, the equation becomes very simple. because you know this, and this QV activation energy is given as a constant, and you know the temperature, but don't forget to convert it into Kelvin unit. And then you know the vacancy number is 2.7 times 10 to the power of -4 times N. So you see, it's not that little, yeah? It's something, you know, in order of 10 to the -4, yeah? It's not like percentage level, but pretty something not easy to be neglected, as I told you, yeah? If you just convert it into the exact number, it is a little bit significant because it's a lot. Yeah, it's 10 to 20 to the power of 25. Yeah, because you have many lattice sites. Yeah, so this is something for you to have impression about. And then we're gonna move on with the second type of impurity, or second type of defects or imperfections of point defects. And this is about impurity. So before we were really talking about a pure metal, a pure material. Now if we just mix it with something, you know, in the reality, we never found a pure something. Even the gold ring, you know, it is not pure gold. It's 99%, 999 of gold. Yeah. So if we have something, you know, the secondary element, we would have two kind of situations in terms of defects or impurity, to be more specific here. And the first type is so-called a substitution element. So basically that means your B element or your B atom is replacing your A atom. So that makes the whole thing is called a substitution defection, imperfection. And the second type is if your second element is pretty small. So, you know, the B element is rather small and it doesn't replace the A element. It just goes into, you know, the gaps. You know, even for FCC, we're having about 25% of the gaps into your structure. So if their radius are significantly different, this will create the so-called interstitial imperfection. And an example is, for example, carbon in iron. This is a typical interstitial imperfection. Yeah, so we will go with some quantitative definition about these imperfections. Actually, they're pretty simple, you know them also. Most likely from your high school, we could go with the weight percentage to describe this impurity, or we could also go with atom percentage for the description of the impurity. So be careful when you just describe your chemical composition of a material. Always specify you're measuring it via a weight percentage, so by mass of the components, or by the atom number or the number of moles of your atoms. So this will lead to completely different results. All right, that's enough for the zero-dimensional point defects. Now we move to line defects. This is so-called dislocations. Actually, dislocations is something you could imagine. So the definitions of this dislocation is they are one-dimensional defects around which atoms are misaligned. Yeah, so this is really something like you know. There are two types of dislocations. One is called edge, and the other called spool. I will show you the figures. So the edge dislocation is something you can see from all this figure. This is 3D, this is 2D. And as you can imagine by the dislocations, if we have a perfect lattice, so they would look like without this one. So by edge dislocation, basically you insert a line of elements or plane of atoms into your perfect crystallographic structure, and this will create so-called edge dislocations. Two important characteristics about edge dislocation. The first of all, this line, so here is so-called dislocation line, because here is the line that you insert this kind of area of atoms. And another thing is called Berger vector. This is a description to basically describe the relation between your misorientated atoms with respect to the kind of perfect crystal. And here I tell you how this Berger vector is derived. The derivation is also rather simple. So if you just abstract this 3D dislocation into a 2D, as you can see, due to this insert of atoms or area of atoms, we create a certain distortion. If we pick a starting point, for example, here, and go to a loop, so this loop will involve this dislocation lines inside, and you will count basically how many atoms you meet or how many grades you walk through. So you remember that number until you come back to your origin. And you do the same again into a perfect crystal structure, with the exactly same number. As you can imagine here, due to the dislocation here, we will feel short by 1 grid or by 1 atom. So then the Berger vector is derived. If you just connect the stopping point to the beginning point, this creates your Berger vector. So as you can see, the Berger vector for edge dislocation is this way. So it is basically perpendicular to your dislocation line. This is why it's called edge dislocation. And the second type of dislocation is called screw dislocation. If you just try to reflect what I said with the Berger's vector and dislocation line, you can already imagine for the screw dislocation, our Berger vector is in parallel to the dislocation line. And how the screw dislocation is created. So it's not by inserting an area of atoms, it's basically by sharing. So if you just share your atoms at a certain position by 1 grid, as you can see here, you will create this so-called screw dislocation because it's done by screwing. So it is not very good work, to be honest, because dislocations may be something you will either love very much or you will hate very much, because this guy is going to create a lot of problems for you. So this is the screw dislocation. And in reality, as you could imagine, nothing is always that perfect. So we could have screw dislocations. So when the Berger's vector is in parallel to your dislocation line, and you also could have some edge dislocation on the other side. This is still screw dislocation, just from different view. I want to show you this picture. So for example, here is a screw dislocation. And for example, here is the edge dislocation. I can also visualize by some animation here. So edge dislocation line perpendicular to Berger vector, and screw dislocation line is parallel to the Berger's vector. And maybe you're wondering what is happening in between. In between, actually, they're so-called mixed dislocations, for which the Berger's vector is neither parallel or perpendicular to the dislocation line. So that's why it's so-called mixed dislocations. So this is most often seen in our materials. So that was schematic drawing for you to understand it. Now I'm trying to show you some, real microscopic pictures. So this dislocation lines are, this cute lines are the dislocation lines. And here is a magnification quite already small, to be honest. It is done by TM. You don't need to know all these terms. It's just, if you just zoom in, but before you zoom into the atoms, you just step out a little bit, you will see these cute dislocations. Okay, this is a slide I will not explain in detail because next week we're gonna talk about it. The dislocations are really so important for our plastic deformation. So that's why you're gonna hear about it in many occasions. Finally, I would like to give you something about interfacial defects. So that is the 2D defects. Actually, to visualize it, also pretty simple. because with the knowledge that you obtained with point effects and dislocations, and now if we talk about planar defects or interfacial defects, it's nothing but stacking your dislocations to a plane. You stack them multiple times with a bunch of dislocations, you would create a so-called interfacial defects or planar defects. So this is a very nice kind of illustration. It's not real. The real thing is on the right-hand side, but this is a nice illustration. One very important notification here you should pay attention is when you just stack your dislocations. If you just stack one dislocation, you don't really change too much of your orientations, yeah, as you can see before, or as you can imagine. If I remove this two, your complete BCC structures or so would still go with a similar pattern. But if I stack many, as you can see, yeah, you can either imagine it's a simple crystal or BCC. It doesn't matter. But if I stack many and many, you see my crystal on the left-hand side is going kind of with this kind of pattern. Yeah. My crystal on the right-hand side is going a quite different pattern already. Yeah. So this is important knowledge for you to know this kind of misorientation, this kind of a rotation of your crystals are creating a situation they don't belong to the same crystal anymore. So that's why we would call this is grain one. So grain is nothing but crystal. You can call it grain. You can also call it crystal. So this, we call this is grain one and this is a grain two. And the only difference is that the orientations or the pattern of alignments are not the same in grain one and grain two. Basically, due to the stack of dislocations that form a interstitial or planary defects, so-called grain boundaries. Yeah, so this is so-called grain boundaries. I hope that is clear because this is a very fundamental concept for all of you in the future because we are not dealing with the simple crystals in our daily life, only for some very interesting and advanced technology. Most of our engineering materials are so-called polycrystals. So polycrystals means a lot of crystals. All right, actually I've already explained you in the previous slide about this grain boundary. So here is again trying to visualize you again. If we, in this grain, our stacking pattern or atom pattern is like horizontal, vertical in that way, but in this grain, it's completely different. You see, we can even measure this kind of misalignment by an angle. So if this angle is very large, we call it high grain boundary angle. And if this angle is rather small, meaning you just distort it a little bit, it's so-called low grain boundary angle or small grain boundary angle. All right, so here is a, again, more zoomed out picture when you just look at your materials. The different colors actually are indicating the different crystals or different grains. They are kind of having a correlation between the certain orientations of your crystals. I will just tell you a little bit more proper definition later. And this is again for you just to visualize when you just look at from your micrograph. This is a polycrystal basically, and how that your crystals or your atoms, your unit cells look like within this material. So for example, this is a sheet metal. For sheet metal, we always gave a coordinate system. We go with the rolling direction, and basically this is X, and we can go this with Y, and we can go with out of plane as Z. So you basically construct a coordinate system. And within the different grains, your unit cell will be arranged either like that, sitting very regularly, or it's rotated like a little bit crazily and like so on. So this is the so-called, let's say, the crystallography orientation. Yeah, and not defined yet, but I will give the definition later. And if you just notice difference between these two, here our unit cells or our crystals are seated in a random way. So they sit like that, like this, and here you can see they're sitting in a regular pattern. They're always in a certain directions with my rolling direction, with my, let's say, sample coordinate. This will tells you why for our daily material engineering materials, we are having most likely isotropic properties. Because although your property in the unit cell is anisotropic, when you just sit randomly to construct a polycrystal, it will become rather isotropic. Yeah, I hope you get it. Yeah, this is only a scale matter. But there could be also cases when they don't sit like a regular pattern. They still prefer to sit in, in a preferred way, maybe not like this extreme, but a little bit different. That will still create some anisotropic properties when you just measure your materials. And for such a thing, we call it texture. So this is meaning the material has a certain texture. Yeah. So we'll not touch too detailed over there. And I would rather to give you, let me see, what about time? Okay, so the time is limited. So I will just give a touch of it. Ms. Wenqi Liu will give you more proper explanation about these parts. So here I'm telling you a proper definition of crystallography orientation. Actually, that is a very mathematical definition. The definition of the crystallography orientation is basically you need to have a rotation matrix to rotate your crystal orientation. So looking like this, crystal orientation, XYZ, or you call it 001 and 100 and 010, to your sample coordinate. So we'll also give our sample coordinate via rolling direction, transverse direction, normal direction. So you can divide it, if you're speaking about 3D materials, this is a 3D printed materials, this is also a little bit different. But the crystallography orientation basically is telling you how do we correlate these two coordinates together. And this is one concept for the polycrystal. And the second concept is so-called grain size or crystal size, let's say. If we have a polycrystal looking like this, we have many of them. The size of that, the size of each crystal or each grain matters. They will decide your mechanical properties. And it's not a unique number. Actually, it goes with a certain kind of distribution function. This is how it looks like. I will not go to details. As I said, you will learn this from the exercise on Thursday. The last part is the shape of it, the shape of the single crystal. They could be very elongated or they could be round. This feature will also make a big impact of your mechanical properties. There are mathematical descriptions about all the three features I'm telling about. You will learn these mathematical descriptions during our exercise session. All right, I think with that, we can come to the end of our today's lecture. We will have a quick summary about the second part as well. Actually, it's rather simple. We introduced you three types of defects, and I'm telling you why we're having defects in solids. And for the line defects, we have different types of dislocations, and these defects are decisive for many mechanical properties. All right, the final announcements would be the corresponding chapters for the second part of our lecture are chapter 3 and 4, and also a few reminders for the deadlines about assignment, Q&A time, exercise time. All right, try to be there.
I have a question.
Yes, exactly. So I even don't. Oh, I still have a few slides later. So go ahead with your question.
Okay. So when I attend today's lecture, I think that this slide looks a little bit different. Is this a new slide for today's lectures?
I don't get you. Can you repeat?
Is this a new slide for today's lecture, which is haven't been uploaded to my course yet, right?
Yeah, exactly.
Okay. So, okay.
I will upload this later. So after this lecture, you will see the slides. Yeah.
No,
If you guys prefer, I could also upload a pre-version of the slides. So you could have basically look at what it looks like. Yeah, that is possible. Yeah.
and
we
also
can do.
I think that also on CISO there is something like a lecture on Friday. So is that a third lecture or something?
Which lecture on Friday?
On CISO there is something on Friday.
There's only one about the December 7th. I don't know what happened with that one.
Exactly. That is a point probably we can discuss a bit because that was arranged not by me but by our, let's say, planning officer or so, due to some conflicts that you might have. I think the driving force over there is about the students from computational engineering. You have something reserved for that week on Monday that conflicts with our lecture.
I see. So lecture is only on Monday and Tuesday, right?
Yeah, that Friday was an exception due to some confliction with a program or something at that time. Could be due to some events and could also be due to the lecture. Yeah, because at that moment we were not sure if the whole lecture will be given online or it will be physical. So if everybody is okay with the Monday, we actually could do a switch from that Friday back to Monday. Yeah, we will go with a, let's say, an announcement or a general discussion in my courses. So if no one says he couldn't go on with the Monday in that week, we will basically switch that Friday back to Monday. I hope that can be still managed. Okay.
Okay.
Good. And something very important. I noticed some people left already, but this is something very important. I would suggest, Wenqi, you probably even send an announcement to all students, because they probably didn't catch this few slides I didn't present yet. Before you go to the exercise session, try to get yourself ready with a certain software. As I told you, we're really giving you some fascinating software training on material science and engineering, but you need to get prepared from your side. And these slides prepared by Ms. Wenqi Liu are giving you step-by-step instructions on how to get those software installed on your computer. If you don't install it, you can also use a remote desktop from Aalto to just directly use it for at least for MATLAB, but you need to get something for MTeX, which is a toolbox on MATLAB. And these are basically the instructions how to do that. Pretty simple, maybe just a few minutes for you to get it done, but try to get there. We don't need to, waste time on Thursday to get you figured on this site. All right. So, I even forgot to tell you the final mystery, huh? I will try to tell you a little bit faster here. So this problem was, the Kepler conjecture was finally resolved, officially 5 years ago, 2015, by the mathematician, so-called Professor Thomas Hills, still alive in University of Michigan. And he exactly followed the approach that pointed out by Professor Todd, and he used a minimization function with 150 variables. It's a very interesting journey for him to get it done. Actually, the whole journey took about 20 years to get this conjecture proved. But now it is proved. So you can now be sure that the best packing of orange is FCC or HCP. This is proven by mathematics. All right, I think that's all, everybody. And we have already answered some questions. If you still have any, go ahead. Otherwise, I wish you a good week and also good afternoon. So see you next week.